Imagine holding the north poles of two strong magnets and trying to push them together. You can feel a physical, invisible resistance pushing back against your hands. The physical effort you expend to force them close doesn't disappear. That effort gets trapped directly inside the system, stored as potential energy. We can apply this exact same physical logic to subatomic particles. Our goal is to mathematically calculate the precise amount of energy stored when bringing two individual point charges together. This diagram outlines our physical baseline. We establish a fixed point in space for our first charge, Q1. Then we position our second charge, Q2, infinitely far away, preparing to move it inward along a straight path to a final target distance of r. We start at infinity because we need a blank slate. Quantifying invisible, stored energy requires a rigid zero-point baseline to measure against. The stored energy in this two-charge system equals the total mechanical work an external force performs, pushing Q2 from infinity down to distance r. To measure this work accurately, the inward external force must perfectly match the outward electric repulsion at every point. We represent this using the differential work equation. But there is a counterintuitive hurdle here. Notice the angle in the dot product is 180 degrees. If we are pushing the charge inward, why aren't the vectors aligned at 0 degrees? It comes down to our coordinate system. Because our position variable, x, increases to the right, any small change in position, dx, inherently points to the right. But to counteract the natural repulsion, our external force must push inward, to the left. The motion and the applied force point in directly opposite directions. Returning to the math block, you can see how the cosine of that 180-degree angle evaluates to -1. This introduces a crucial negative sign into our foundational equation. If we fail to respect the strict rules of coordinate geometry and vector direction, this initial equation is flawed, and our entire calculation of work will collapse. With our differential equation correctly built, we find the total work by integrating across our physical boundaries. We set up the definite integral, paying close attention to the limits. The journey begins at infinity and terminates at our target distance, r. Pause the video for a moment. Try using the power rule for integration on the negative inverse square of x to solve this definite integral on your own. Integrating -1 over x squared yields a positive 1 over x. When we apply our physical limits, we get 1 over r minus 1 over infinity. Mathematically, as distance grows toward infinity, that second term approaches 0, simplifying the expression. This leaves us with a final expression. Total work equals the product of the charges divided by 4 pi epsilon naught r. This is the exact literal accounting of the physical effort trapped within the system. This result represents more than a series of calculus steps. It quantifies the persistent mechanical energy that defines the state of these two point charges. Because this work is stored, we formally rename it. As shown in this boxed equation, the total work calculated is defined as electrostatic potential energy, represented by the capital letter U. But there is a trap here that catches many students. Unlike electric force or electric fields, potential energy is a scalar quantity. It has magnitude, but no spatial direction. This handwritten note at the bottom highlights the golden rule for scalar energies. You cannot determine direction with a vector arrow. You must input the specific positive or negative algebraic signs of the charges directly into the formula. The math reflects the physical reality. If both charges share the same sign, the final energy is positive, indicating mutual repulsion. If the charges have opposite signs, the energy is negative, proving that the system is bound together by attraction. This derivation provides the technical framework for calculating the binding energy of any atomic system. Accuracy depends entirely on applying the algebraic signs of the charges with precision.